In section 6, we're continuing a discussion of functions in general. We're going to be looking at exponential functions specifically. So we're going to be looking at how to evaluate them, how to write their equations, and how to use compound interest formulas. The last piece, exponential functions with base e, will show up in the homework, not in the notes necessarily. E is a number you should have had experience with with that number in the past. In the homework, we're going to look kind of specifically at where E comes from and why it is what it is. But that's why we save it for the homework. It's a bit of an exploration thing rather than just having it in the notes. So, what is an exponential function? This is an example. F of x is 2 to the x. So an exponential function is when you have a base that's a constant, it's a number, and you're raising it to something with an exponent involved. So in this case, 2 to the x. This is an example of exponential growth because it's getting bigger, right? It's just going up. So exponential functions can be growth or decay, where the graph would look more like this. Exponential decay would be something like 1/2 raised to the x, okay? And so you can see you just plug it in and you get out whatever you need to. So if you plug in -2, that would be 2 to the -2, or 1/4, right? So like most functions, you can just plug in x values, see what the corresponding y values are, and use that to determine what a graph would look like or build a table that way. But that's all an exponential function is. More specifically, it can be in the form a times b to the x. So that last example was just 1 times 2 to the x, right? So 1 times 2 to the x, a was 1, b was 2, just raised to the x power. So if we look at a few things like this, which of the following are not exponential functions? F of x is. It's a constant raised to an exponent that has variables involved. G of x is not. G of x is a polynomial or power function. You could classify it either way. H of x is, right, 1/3 to the x. And then J of x, we're going to say new. Basically, b has to be greater than 0, right? To look at these, we don't want our base to be negative, just because that can create the funkiness that as you plug in x values, like if you plug in 1, then 2, then 3, then 4, then 5, the values you're getting back are constantly like alternating between being positive and negative, and we're just not going to mess with that. So then, evaluating. Evaluating an exponential function is no different than evaluating any other function that we've looked at. So g of 2 just means take the function that you're given and plug in 2 for x. So this is 6 times 3 to the 4th, which is 6 times 81, which is 246. So evaluating these is the same as any other function you've ever evaluated. This means plug 2 in for x and simplify as much as you can. So then writing equations. So word problems are going to be what we're going to play around with in this case, but how do you write equations for exponential functions like this? So in 06, 80 deer are introduced into a refuge. By 2012, 6 years later, the population had grown to 180. The population was growing exponentially. Write an algebraic function n of t representing the population n over the time t. So this sentence right here, it was growing exponentially. If you're not told that it's exponential growth, then you'd have to play around with it. You could try, like maybe it's a quadratic, maybe it's a cubic, maybe it's a trigonometric function. You could try modeling it a bunch of different ways. We're just told it's exponential, since that's what we're talking about in these notes. So how are we going to go about figuring this function out? We know that n of t is an exponential function, so it's going to be something like this, ab to the t. We know that at time 0, right, AB to the 0, we know we've got 80 deer, right? So times 0 would refer to 2006. So b to the 0 is just 1, so this is just a equals 80. So then we also know that at times 6, so that's 80b to the 6th, we've got 180. So then b to the 6th is 180 over 80, which is what? 90 over 40, 45 over 20, 9/4. So to solve for b, you take the 6th root of each side. So b should be the 6th root of 9/4, which is approximately 1.1447. So then the function that would give the population of deer n of t is 80 times 1.1447 to the t, based on the information we've been given. So writing these equations, use that general form of an exponential function, and then if you've got 2 points, plug those 2 points in and figure it out and go from there. So in a situation like this, it's pretty much the same. We know y equals ab to the x, so plug in the 2 points. So we've got this. Remembering that this is 1 over b squared, right? So this is really 6 equals a over b squared, so then 6b squared is a, which allows us to say 1 equals 6b squared b squared, so 1 is 6b to the 4th, so then 1/6 is b to the 4th, and then similar to the last problem, what we end up with is b is the 4th root of 1/6, which is roughly 0.6389. Plug that in right chon, and that lets us know that a is going to be roughly 2.4492. So we get this. Y is 2.4492 times 0.6389 to the x. So it's a system of equations, basically. And if you graph this one, you'd see this is an example of exponential decay as opposed to exponential growth. So writing the equation based off the graph, really what we can do is identify points and then use the same exact process we've done before. So in the graph, you can see we've got the 0.03, we've got the 0.16. Right, if we plug those in, we've got 3 equals ab to the 0, meaning a is 3. And we've got 6 equals ab to the 1st. So 6 is 3b. b would then have to be 2. So our equation is y equals 3 times 2 to the x. So that's the same exact process we used in the deer problem and in the last problem where we were given the 2 points. And in this one, it's always a system of 2 equations. It works out a little bit easier when you know the y-intercept, because that's basically going to give you a immediately. Okay, for this one, it's the same idea. You're getting 2 points, you're being asked for the equation. It's really just how do you ask the calculator to do it. We've done the regressions before, so you just need to remember how to put the things into your lists. I've put the 2 points in. Once the points are in, you come over to calculate. If you go down to the 10th option, the 0, xpreg, that is an exponential regression. You get your equation that way. So you can see it's going to be 12 times 1.85 to the x. So the idea of regressions is still very much there, and you can do regressions for all different types of functions to include exponentials. Okay, so then the last piece we're going to look at in these notes, compound interest formula. So this is it, and again, this is something that ideally you've seen before, but if not, this is the amount that would be in an account after time t, P is the principal, however much you started with, so it's like the initial amount you put in a savings account. R is the rate, called the annual percentage rate. N is the number of times it's compounded in a year, and T is the amount of time that has passed. So that's what the compound interest formula is. Principal amount, APR, number of compounding times in a year, and T is then the measure of years. So how do we use that formula in a situation like this? So the formula A of T, so the principal, the initial amount is 3,000. The rate is 3% over 4, because it's compounded quarterly, meaning it'll be compounded 4 times in a year, to the 4 times T. So then A of 10, you plug 10 in for the T right there and see what you get, right? And in this case, it should be about $4,045.05 after 10 years. So that's using the compound interest formula, right? So you need to identify the principal amount, the rate, the number of compounding events in a year, and the time. That'll tell you what it's worth. So this is another example, right? You should take a minute to read it. I'm not going to read it to you. It's a lot of words. So you can pause, read it. May or may not have actually paused, but here we go. So this is just looking at it from a different perspective. Same formula, more just if you know what you want an account to be after a certain amount of time, and you want to find out then how much should you invest in the beginning, what does that look like? So in this case, we know we want to end up with 40,000. We don't know the principal. We're guessing the rate is going to be about 6%. It's compounding twice a year, so it's going to be 2. And in this case, we're looking at 18 years, right? She's starting this account for her granddaughter. So college is going to be an issue in 18 years. So this is the equation we have. We need to solve it for P. So first step, we get 40,000 is P times 1.03 to the 36. Divide each side by 1.03 to the 36. You get that principal amount needs to be roughly $13,801. Okay, so if you invest that $13,801 and it does indeed grow at that 6% rate, you get your 40,000 after 18 years. So that should have been primarily a review of exponential functions. Again, we're going to talk about this guy in the homework, just again to try and highlight what E is and why it is what it is. But that's it. You should spend the rest of this time working on your homework. We will spend class time Wednesday working on section 6 as well.